Hey everybody, welcome back to particle motion. Today we are going to look at a very special case of particle motion that is called free fall, which is a topic in physics that you deal with quite a bit. So if you have taken physics and you've done kinematics or the equations of kinematics, you are very familiar with free fall. This is a oversimplified version of free fall because after all, this is calculus class, not physics class. So I want to talk about just kind of the basics of free fall here with you, and then we're going to do an example. One of the things I mentioned earlier is that in calculus, we're always either going left, right, or up, down. In the case of free fall, we're talking about an object that has been kind of tossed into the air, and the only thing affecting it at this point is gravity. In calculus, we are in a vacuum, in outer space, on ice. There's no friction, there's no air resistance, there's nothing else going on but gravity, right? So we don't have to worry about things like air resistance or friction or anything like that. It kind of really simplifies it for us. We have talked about how it would only be a straight up and down line. So if something is thrown, it's going to go straight up and then straight back down again. Or if something is dropped, it's just going to go straight down. You'll notice that this flight path I have drawn here is kind of a wider curve. The reason for that is I'm about to label it up with some important information. But in general, in calculus, when we throw something up, we're going to throw it straight up. We're not going to throw it off at an angle so that it makes like a big arc. All right, so a couple really important things to know. That when an object is in free fall, the only thing acting on it is gravity, and gravity is the acceleration due to gravity. So if something is in free fall, the acceleration is always constant. If they're asking you for the acceleration, you better be reporting a number. And depending on your system of units, that number will be different. So if you're working in MKS, meters, kilograms, and seconds, it will be negative 9.8 meters per second squared. In other words, the velocity is increasing in the negative direction by 9.8 meters per second every second. In other words, gravity is trying to pull it down. Right? That's where the negative comes from. If you're in the FPS system, the American system, annoying. Every time I see a problem with feet in it, I get annoyed immediately. Then our acceleration due to gravity will be negative 32 feet per second squared. Okay, so as long as you're dealing with gravity, if they ask you acceleration, your answer better be one of these two things, or you done messed up. Go back. Okay, things we already know. The sign convention is that velocity is positive when it's moving up, negative when it's moving down. So in this case, if I have an object here and it leaves the ground, I'm going to call this t equals 0. It's going to travel up, up, up. On the way up, it's going to have a positive velocity. It's going to hit a peak, and then it's going to travel back down, down, down. On the way down, it's going to have a negative velocity. I'm going to call this time at the bottom star. So star being the total. Sometimes they call it the total flight time or the total time in the air. Right? And that is sometimes a question they ask, which is going to become really easy for us to answer. Okay, so positive velocity on the way up, negative velocity on the way down. And really, really, really important are these last two facts I have here. Velocity is 0 at the top. So we talked about this a little bit the other day when we said that in order to change direction, an object has to stop for an instant, right? If it's moving to the left and then suddenly it's moving to the right, it must have stopped. And we saw that on our sign charts. In order for there to be a sign change in velocity, there was always a 0 in the middle. Okay. So right up here, we call this maximum height. And we know two things about maximum height. The velocity has to be 0. So they ask you to find the maximum height of an object, take the velocity and set it equal to 0. That's going to give you your max height. Now, little word of warning. A common mistake I see people make. If they say how long was it in the air for, people take the velocity and set it equal to 0, thinking it's going to give them this down here. And their defense is, well, it hit the ground. It obviously stopped. Every physics teacher gets a chill up their spine when you say that. Yes, it did hit the ground, but once it hits the ground, it's no longer in free fall, because free fall is only under the influence of gravity. So right here, If you put this time in right here, it's going to give you the velocity that it had when it hit the ground. Like how fast was it going when it hit the ground? Once it hits the ground, free fall party's over. So when it's in the air, there's only going to be one time when the velocity is 0, and that's going to be up here at this maximum height. The other thing we know about maximum height is that this is a symmetrical flight. Gravity is the same on the way up as it is on the way down, right? Gravity's pulling it down. So it's slowing down on the way up and then it's speeding up on the way down. So we have this symmetrical situation. So at the top, the time is always going to be 1/2 of the total flight time. So if the total flight time is star, the time at maximum height is going to be half of that. Right. Time is kind of the great uniter between all of our equations. If we have an equation for position, velocity, and acceleration, they all have time in them. So if you want to know when the velocity is 0, they'll say, like, how high did it go? Well, if we can figure out when it was at its maximum height, then we can plug that into position. Or what was the acceleration when the displacement was this? Well, find out when the displacement was that, and then take that time and plug it into acceleration. So we're always going to get the time when something happened, and then come back and use the other equations to answer their questions. Okay. Another thing I want to point out here is the acceleration thing that we had talked about. We talked about there's 2 ways to have positive acceleration or negative acceleration, right? This acceleration is always, always, always negative. Notice, on the way up, it has a positive velocity, yet the acceleration is negative, right? This thing on the way up is slowing down. We know that because it's trying to travel up, but gravity is saying, no, 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 come back down. So as it gets thrown up, it's on the way up still. It's still moving up, but gravity starts winning the battle. Right? It's right up at the top here that gravity finally wins the battle. It takes a pause for the cause, and then on the way down, it still has negative acceleration because now it has negative velocity. It's traveling down, but it's speeding up. And again, worth mentioning that we have a symmetrical path here. So for example, if it was whatever velocity it has here, let's say the velocity here is cloud. If you go straight across your path, the velocity here is going to be negative cloud, right? It's going to have the same speed on its way up as it does on its way down at all these varied points. It's a mirror image when it comes to speed. Velocity, all velocities on the way up are going to be positive, and on the other side, you're going to have the same velocities, but they'll be negative, because that's just denoting that it's moving back down again. Okay, so we will see questions that say, when was the velocity equal to 5? Okay, that's only going to be one time, right, on the way up. Well, when was the speed equal to 5? It's going to be 2 times, once on the way up, once on the way down. So you have to be careful with those questions. Big difference between velocity and speed. Okay, let's do an example so we can put this to use. Okay, so a rock is propelled upward with a launch velocity of 160 feet per second. That is quite a rock propeller. Okay, so I know I have a velocity of 160 feet per second. They gave me a position and they want to know how high this thing goes. In other words, they want to know what's S of t at a very specific spot at max height. So what is the position at maximum height? I can look at this graph and tell you that it's 400. Right? But obviously they're not going to give us the graph. Why would they do that, right? So from this graph we can see that at, oh my goodness, that at 5 seconds, it hits a maximum height of 400 feet. But let's find that out using calculus, shall we? Okay, so all I need to do is figure out when is my position at maximum height. Well, to get maximum height, I know one thing about this point right here. Well, I know 2 things. Right? It happens halfway through, and it happens when velocity is equal to 0. Well, they happened to give me a position function, so I can find an equation for velocity. So if my position is 160t minus 16t squared, then my velocity is going to be 160 minus 32t. If I can figure out when that's 0, then I'll know that's when it's at max height. This is what I mean about time being the kind of connector that's going to move us between position, velocity, and acceleration. So I can figure out when it was at maximum height here. So all I have to do is solve 160 minus 32t is equal to 0. According to this graph, we better get a 5. Okay. So if I take the 32t to the other side, to avoid negatives, as I'm wont to do, divide by 32 on both sides, bingo, bango, we get that time is equal to 5 seconds. So this is telling me that at t equals 5 seconds, it's at max height. So now I know when it was at maximum height, thanks to my velocity equation. The question is, am I on the wrong slide? I sure am. Oops. The question is, let me rewrite that for you since I accidentally bumped myself forward. When does velocity equal 0? So that's going to be 160 equals 32t, or when t equals 5. So at t equals 5 seconds, it reaches max height. Okay, so again, we knew that from the graph that it was at 5 seconds. The question, though, is how high does it go? So now that I know when it gets to its max height, all I have to do if I want to know its actual position at that time is pop it back into my displacement equation. So now I know I need S of 5 because that's when it hits max height. So I get 160 times 5 minus 16 times 25. So let's see. Better get 400. We're in trouble. 160 times 5 is 800. And 16 times 25 is 400. So we get 400 feet. Again, if you have a calculator, you're going to graph this. You can see it, but they're not going to give you a calculator on a question like this. Okay. Now let me erase this slide. Okay, so again, left the ground with a launch velocity of 160 feet per second. So in other words, when it left the ground, it was going 160 feet per second. It says, what is the velocity and speed? So they want both when it is 256 feet above the ground. So 256 feet above the ground is a position. Again, time is the thing that's going to pull us. They're giving us information about position. They're asking us about velocity. So I know I'm going to need a velocity equation, and I already found it. Found it on the last slide. So if I can figure out when my position is 256, then those are the times I need to go put back in my velocity equation because they're asking about velocity. So all I have to do is take my position equation, 160t minus 16t squared, and say when is that equal to 256? When does that happen? Well, this is a quadratic equation. There's going to be two answers, right? It's going to be at a height of 256 twice. Once on the way up, once on the way down. Don't ignore the two answers. So let's see. I can divide all of this by 16 to make my life a little bit easier. I'm also going to write it in standard form. So let's see. Let's do this. Negative 16 squared plus 160t minus 256. And then I'm going to divide everything through by negative 16. So I'll just have a nice neat t squared right here. And then this will be a minus 10t and a plus 16. And I believe then that this should be factorable to t minus 8 and t minus 2. Which would give you a positive 16 here and a minus 10 in the middle. So it's telling me that there are two times that my position is 256. 2 seconds and 8 seconds. Again, let's go to our graph. 256 is somewhere in here, and notice happens right around 2 seconds, happens again right around 8 seconds. You can see it from our graph. All right, so I'm out of space. I'm probably going to have to clear this, but now that I know what the times are when this happens, when it's 256 feet above the ground happens twice, at 2 seconds and at 8 seconds. Okay, well, what do you want to know about those times? They want to know what the velocity and the speed is. So all I have to do is take my 2 and my 8 and pop them into my velocity equation. So let me grab another color I'm going to do V of 2. So I get 160 minus 32 times 2. So that's 160 minus 64, or what, 96 feet per second. Okay. On the way up. So right here, it's 96 feet per second. Now, if I put in V of 8, it better be mirrored, right? I'm expecting V of 8 to be the same number, except that it's on the way down, so better term will be negative. So over here, I have 160 minus 32 times 8. So let's see, 32 times 8 is 256. 160 minus 256 is bango, negative 96 feet per second. So here's my velocity and speed. So my velocity at 2 is 96. My velocity at 8 is negative 96. The speed in both places is just 96. So we might say, let me erase a little bit here. Okay, so to answer this, we might say, what is the velocity and speed? What is it? We would say at t equals 2, velocity equals 96 feet per second, speed equals 96 feet per second, and then at t equals 8, velocity equals negative 96 feet per second, speed equals 96 feet per second. Make sure you give both of those because they ask for both. All right. Oh, this is a beautiful question. What is the rock's acceleration? Well, we know it better be constant, and I know I'm in feet per second, so I know I already know the answer. But calculus, of course, wants us to prove it. So if I need the rock's acceleration, that's the second derivative of position. So if my position is 160t minus 16t squared, my velocity is 160 minus 32t, my acceleration is going to be negative 32 feet per second squared. Boom, 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 boom. Now, when I do these problems, I think I mentioned this the other day, the first thing I do is get all three equations. So I have position, let me take the derivative and get velocity, let me take the derivative and get acceleration, so that I have all those equations right in front of me, and all I have to do is grab the one that I need. Didn't do that here because I couldn't keep them on the board for you. But again, if you get anything other than a constant, and the very specific constant that you're looking for in free fall, something's wrong. Now again, if you're not in feet per second, you're not going to get 32. And if you're not in meters in seconds, you're not going to get 98 or 9.8. But you should be getting those numbers most of the time. All right. So I am going to pause for the cause right now because I've been talking to you for 18 minutes and I know you're probably sick of me. I will post another video of going through this second example so that you can see another example of how free fall works if you'd like to. For now, let's all take a deep breath and get our eyes off the computer screen. I will see you later.